Hey, welcome to this video. Here we're going to be talking about monitoring and observability. Now, the reason that I want to cover this topic is to help you avoid a stressful situation where you find yourself troubleshooting an outage with some software without the information you need to find out what's going on and fix it. And also, hopefully the knowledge in this video will help you avoid a situation where you're overpaying an expensive SaaS vendor who promises to solve all of your monitoring problems. All right, let's start with observability. Observability is a measure of how well a system's internal state can be inferred from what you know about its outputs. So, for example, this is a system. What do you think's going on in there? I'll tell you what, any guess that I might make about what's happening inside that room would probably be wrong. So this is not a very observable system. What about the human body as a system? Here's a picture of a guy. Based on this picture, how healthy do you think he is? He's got gray hair and some wrinkles, so I'm gonna make a guess that he's over 60 years old. Is he close to having a stroke? I would guess not, because when you have a blood clot in your brain, sometimes that can cause one side of your face to become slack. And the tautness in this guy's facial muscles look symmetrical, but I don't know if that's a perfect test, so I'm not really sure. How's his heart health? He's not pale, so he probably has good circulation. But then again, he is older, so maybe he has more of a buildup of plaque in his arteries. I don't know. I'm not really confident saying. Is he diabetic? Or is he close to an allergic reaction? Are his kidneys working? For each of these questions, there are some clues that we could gather from just a picture of this guy's face to inform the guesses that we might make. But in general, just going off this picture, I'm not very confident in any of the inferences that I just made about this guy's health. In order for me to be more confident, I would want more data. Since I'm not very confident making inferences about the internal state of this guy based on this picture, that means that at the moment, this guy's body as a system is not very observable. But if I had more information, then I could make better guesses, and this system would be more observable. Well, monitoring is the process of collecting and storing and analyzing data about a system's outputs. So as we collect and store and analyze more data about a system, then we get more knowledge, and more knowledge allows us to make better inferences. And if we can make better inferences from the knowledge we have about a system, then the system is more observable. So observability is a property of a system. Monitoring is a process for increasing the observability of a system. All right, well, how do we actually go about collecting data for a system? We do that using instruments. Instruments can record system outputs or system states. For example, this here is a glucose monitor. You can prick yourself and you could read your blood glucose. If I had readings of that guy's glucose from before, then maybe I could tell if his blood sugar was spiked or super low. And maybe if I had readings about that over time, I could tell if he was behaving in an abnormal way and therefore probably is diabetic. In fact, I could probably get enough information to give me great certainty that he is in fact a diabetic. The questions I asked earlier about whether someone is close to a stroke or their heart health or whether they're close to an allergic reaction, information about someone's temperature may be taken with a thermometer or an EKG or blood pressure, give you a lot more confidence making those inferences. One thing that I want to note here is that all of these instruments on this slide, except for one, are structured data, which is to say they can easily be represented in a table, like a spreadsheet or a SQL database. With glucose, it's a series of measurements over time. Same with blood pressure, same with weight, kind of the same with EKGs and temperature. But pictures can absolutely give us information about someone's health. It's hard to put a picture into a spreadsheet, and pictures can tell us a lot more than just one thing. For example, I can tell that between these two pictures, this guy is leaner, but he's also potentially more tan, or it's just better lighting. And I don't know, if he had like a visible tumor on the right side, then this might mean that he got cancer. Anyway, so there's lots of different kinds of data that you can extract from an image. And so I just want to point out that not all instruments yield structured data. All right, so instruments help us record system outputs and system states. Instrumentation is the process of installing instruments into our system to record the data about the system states and outputs. So if you want to start recording information about a system, then you should instrument that system, or in other words, you should install instruments into the system. Now, not everything can be observed directly via an instrument, hence the need to make inferences. So, for example, here's a rocket engine. Rocket engines are really hot inside. If a rocket is taking off or flying out to space, then it's really important that the engine doesn't overheat, or else mission's over, money wasted. So it might be helpful if you could know the temperature inside the rocket so that you could react to that and maybe back off on the thrust or something. So yeah, maybe we could put a thermometer in the rocket engine and use that to measure the temperature. Well, the problem with that would be that the rocket engine can get really hot. And so if you put a thermometer in there, it could melt the thermometer. And so, potentially, the best thing you could do is place a thermometer maybe on the outside of the engine and take temperature readings there. And based on those readings and what you know about how heat transfer through metal sheets work and the anatomy of your rocket, you could use all that information to then make an informed guess about what the actual temperature in the rocket engine is. By the way, observability is a term from a branch of mathematics called control theory, and this exact problem was one of the historical questions that control theory was used to study and allowed us to land a rocket on the moon. Now, one thing to say about monitoring and instrumentation is that once a system is far away or you don't have direct access to it, for example, your rocket is out in space, then how do you actually get the recordings from your instruments to have insights into what's going on? Telemetry is the process of recording and transmitting the readings of an instrument. So when people talk about telemetry data, they're talking about the data that they're recording and monitoring in a system. All right, we've talked about some systems. We talked about the human body. We talked about a rocket. Software engineers monitor software systems to detect, diagnose, and prevent problems in their software and identify strategic opportunities to improve it. So, for example, this is an app that I built called Rootski. When it works, Rootski has a search bar that you can use to search for Russian words. And if you click on one, you can learn about the roots in that Russian word, which is a nice tool for studying Russian. But look, Rootski's broken. It's not finding any words when you search for things in the search bar. What is wrong, and how long has it been like this? I don't know. I never actually instrumented it. So yeah. But if I wanted to go back and fix it, what could I do? There's a few types of observability data that are used. When we were talking about the human body, you could imagine that there's some standard things that you want to measure. And the same is true in software. There are some common types of data that you can collect about your software system to improve its observability. One is metrics, another is logs, and another is traces. Metrics are numerical and they tell you what is going on. For example, with the human body, a metric might be my blood glucose. And if my blood glucose is incredibly high, then that probably means something's wrong. Similarly in software, if we're talking about a REST API, I could count the number of error response codes being returned by my app. And if I'm getting a spike in 400 or 500 errors, then something's probably wrong. But once you know something's wrong, you don't necessarily know why it went wrong. And that is what logs help with. For example, if your application crashed, then it probably raised an exception. And with that exception, there's probably a traceback. And that traceback is recorded as a log. Logs generally are not structured the way metrics are, but they can be somewhere between unstructured and semi-structured. And if you can find the relevant logs about the error that's happening, then you can get an answer to why the problem happened in your app. But the key there is if you can find the relevant logs. If you have a complex software system, what logs should you even be looking at? I mean, you might have a lot of components of your system generating logs, and so traces help answer the question of where in your system the error actually happened. And if multiple components are involved in an error in your system, traces can help you find all of those components. Now, these are the main 3 data types in observability, but this is a field where a lot of innovation is happening. And so, for example, there are other data types like exemplars and continuous profiles that I won't go into now, but just know that they exist. And know that certainly the types of data you can record about the performance of your software are not limited to these 3 things. Also, this is a good point to say that this absolutely still applies to AI and ML software too. Software that uses ML to make an inference or AI to generate something is still software. And I think a lot of people in the MLOps space get turned around and lose focus when they start talking with specialized ML software vendors. And yeah, tools that are specific to AI and ML can be great, but I will say that in my experience, 80 or 90% of issues that have happened in AI and ML systems that I've worked on have actually just been classical software issues, like the service is crashing or the service is overloaded. And so using these 3 types of data in the same way that traditional software systems use these 3 types of data, I still believe is where most of the value in observing machine learning systems is. And again, I'm not saying that observability tools don't have their place, but I also think they're the wrong thing to focus on first when it comes to monitoring machine learning systems. All right, now that we've talked about all this theory about observability and monitoring, let's talk workflows. And what's nice about this is the workflow that I'm about to show you is vendor agnostic. Now, the tools used in this workflow are certainly locked in to AWS, but whatever observability tool you end up going with in the future, know that this workflow is roughly what you should expect to use the tool for. So here's an API. This is an API for uploading and downloading files to the cloud. What if there were an outage in this API? How would we detect and fix that outage? Well, this process has 2 steps. Step 1 is finding out that something's even going wrong. It would be really nice if you could get an automated alert whenever something breaks in your app, or even better, before something breaks but is at risk of breaking. It sucks to be the last person to hear that the thing you built is broken. And unfortunately, engineers are usually the last people to hear when the thing is broken because, the engineer writes code, they deploy it to somewhere, and then end users start using it. And the end users don't typically have a direct line of communication with the engineers behind a product. So maybe they're using a website or hitting an API and they're getting errors. They may reach out to a support team or complain to the leaders at a company. And then by the time you hear about it, leaders have had lots of time to get worked up about the problem and get angry. And now they're waking you up with a phone call at 3 a.m. telling you that your thing is broken. It would be really nice for you if you set up automated alerts to tell you when something's at risk of breaking so that you can be the first one to know when your system goes down or is at risk. All right, so once you know there's a problem, step 2 is to investigate the problem. You can't predict every way that your system may break. And honestly, even though there are lots of things you can predict, I think up front, it's often a waste of time to predict all the ways that your system could break because it could be for a million different reasons. Now, there are some common ways that all systems tend to break, and I put those things into a separate category. However, if you collect a lot of relevant unstructured and structured telemetry data, then when the time comes that you need to investigate a problem, if you properly instrument your system so that you can collect a variety of structured and unstructured telemetry data, and especially you should make sure that data is organized, then you should have the easiest possible time doing an ad hoc analysis trying to find the root cause of the problem. And once you can find the root cause, then you can fix it. So those are the 2 steps. You find out that there's a problem, and then you do an investigation to find the root cause. Once you know the root cause, you're golden. All right, so getting an alert, I think, is intuitive, but what about this ad hoc investigation process? What does that look like? I would start by trying to understand what the alert was that just went off. Alerts are built by taking some sort of metric and defining a threshold where you get an alert if it exceeds or goes below the threshold for too long. So for example, here's an alert and it looks like the number of 400 errors has gone over this threshold of like 45 and has stayed there for a while. Okay, so the problem has something to do with 400 errors. That's a really good insight already. But now we need to know, where are these errors happening? Like maybe we have a lot of components in our system and maybe we have a lot of systems. All of those could be producing 400 errors. It would be nice if we could narrow this down. Well, there's actually a lot of ways that we could answer this question, but one really slick way is by using traces. So here is a query where I'm querying for requests that had /files in them, because that'll narrow it down to this files API, hopefully. And I'm searching for 400 status codes, so status codes between 400 and 500 exclusive. And check it out. When I run this query, I get a bunch of results, and here's a bunch of 422 status codes. All right, so it's not even scattered 400 status codes. It seems like it's specifically 422 status codes. That's really insightful because 422 is a status code for unprocessable input into an API. So it sounds like somebody somewhere is sending something to our API incorrectly. But what actually is a trace? I think the next slide illustrates it very nicely. So a trace is a data format that captures all of the services involved in processing a particular transaction. So that could be like an API call, going from a client to API gateway to AWS Lambda, or it could be an event flowing through an event-driven system. But anyway, I never told you how the Files API was actually deployed to AWS, and you might not have known that if you were debugging a problem caused by a service that somebody else develops and owns. But if you can look up traces, the traces will give you a really good idea of what the architecture looks like. In other words, they tell you where to look for the root cause of the problem. That is super cool. Now, this architecture here is clearly a distributed system. We have a request going to an API gateway, which then calls AWS Lambda to invoke a Lambda function to process the request. So there's a few different hops involved. And this view on the bottom right shows us a timeline of exactly how long each component of the system was doing processing and in what order when handling this event. It looks like the API gateway itself is returning the 422 status code. Awesome. And technically, the Files API handler function, this is the Lambda function, is returning successfully. So it sounds like the Lambda function is successfully returning information about a 422 response. But we can see that somewhere in the Lambda function, there's a fault, which is to say there's probably a runtime exception happening in this Lambda function. Well, sweet. We know that API Gateway and Lambda are involved, and we even know that there's an exception happening within the Lambda function. So now we know where to look to understand why the 422 errors are getting returned. We're getting close. Okay, so software running in the cloud produces logs, aka print statements. And you might not think about this if you're used to developing applications locally, but when you deploy an application, it's obviously no longer running on your laptop. So you're not just seeing a terminal feed full of print statements. There might be tons of instances of your application all running at the same time, all producing logs. And if you don't store those logs in an organized way, good luck finding the logs that are relevant to an error of which you're trying to find the root cause during an incident. The logs in this sample application are filled with rich metadata, including the ID of the trace that we were looking at in the previous slide in the request that produced them. So we can look up the logs that were generated in the exact request that we were just looking at on the trace page that produced the response code. So yeah, we take the trace ID and we plug it into this query language to query a massive repository of logs to find exactly the logs we're looking for, and check it out. Some logs get produced, and one of those logs is an error log. Error logs are long, so let's look at a prettier view of it. Look at this. Within the log, here is the traceback, and it looks like the traceback, yes, was a request validation error. We might have thought that would be the case because it's a 422 response, meaning the request was somehow bad. Okay, so this traceback is telling us exactly how the request is bad. It looks like we're missing a query argument called prompt. Okay. Well, what were the query arguments that they passed in? Presumably, when you have a view like this, you can just scroll up and look at the earlier logs and check it out. Here's a log that logs exactly what the inputs to the request were, and it looks like no query params were passed in this request. Now look, we've identified that this route requires query parameters, and this earlier log shows us exactly the query parameters that were sent. And it looks like none were sent. So we found the problem. And now, of course, this is just one request. Maybe there's multiple ways in which requests are failing. So we could sample a few other logs for a few other requests and just get a sense of that. So that's it. We found the root cause of this incident. And if we were doing this real time, this would be a very quick process if we had all of this well-structured, organized telemetry data of these various types. And there's so much more you can do if you collect this data well. For example, we found out that these query params were empty for this particular request, but maybe there's a lot of different invalid requests coming. So it'd be nice if we could at least check to see if this is the only kind of failure case that's happening. Well, you saw that there's a rich query language to query different types of logs. And guess what? Because there's this JSON object in the logs, this log is considered to be semi-structured. And so we can actually use a SQL-like syntax to directly query out query params across many different requests. Also, now that we know what components are involved in the system, there are a lot of metrics that you would ideally collect about every single component. So you could continue your exploration to see what impact this outage has had on the system, looking at things like latency and CPU utilization and 500 errors. So there's a lot you can discover with metrics about the different components, and you can even generate metrics by querying structured logs. Now, if you come up with some queries that you really like that give you good insights, then you could actually capture those queries as widgets in a dashboard. A dashboard is basically a chart that shows you the behavior of your system or different parts of the system. And the dashboard is composed of these plots called widgets. And each of these widgets is powered by a query, either to logs or to metrics or something else. So if you have queries that are particularly insightful and you put them into a dashboard, then the next time something like this happens, you can quickly get it all in one view. And for people who aren't familiar with the query language, for example, you in the future when you've forgotten it, or just people who aren't familiar with your system, like someone from another team, dashboards give you a way to basically produce a package full of real-time insights that you can share to make this analysis easy for other people. And by the way, you can get crazy with dashboards and do things like custom HTML and JavaScript and add tables and buttons. It can get pretty fancy. All right, so this has been a root cause analysis workflow that we've just gone over. Let's recap some of the terms we just covered. Observability is a measure of how well a system's internal state can be inferred from what you know about its outputs. So you want to be able to infer what's happening inside of a system, but you're unable to do that if you don't have good knowledge about outputs of the system. Monitoring is the act of collecting, storing, and analyzing data about a system's outputs or states. So monitoring is basically the process of increasing your knowledge about what's happening inside of a system, aka increasing your observability. And the way that you do monitoring is through instrumentation, the process of installing instruments into our system to record that data, whether unstructured or structured, about system states and outputs. Nice. So now that we've covered all this, if you're building a software system, or if you want to build a software system, hopefully now you believe that you should set up instrumentation for that system before a problem happens so that when it does happen, you're equipped to go troubleshoot it. But there are some common questions, and you might have some of these. How do you actually instrument your software? And what data should you even collect in the instrumentation process? And if you collected a bunch of data, how would you know what to alert on? Because there are a lot of alerts you could make, and your system is probably unique with the business logic. Ideally, you have business logic which differentiates you. Is this going to cost a bunch of money and developer time? Yes. Observability and monitoring and instrumentation is hard enough of a problem that there is a massive software vendor space out there to solve all of your monitoring needs. And so the second you Google observability tools for the first time, you're gonna get put on an advertising watch list, and you'll be hammered with inbound emails from people like these guys. And yeah, by the way, most of them can be super expensive. With monitoring, the 80-20 rule applies. A lot of companies or teams or products don't even have any monitoring set up, or at least not the fancy kind of monitoring workflow that I was just showing you here. So if you set up any monitoring at all, you're already way ahead of the curve. Whatever cloud you're using usually has a rudimentary set of tools for doing monitoring and observability. And of course, the bulk of this course focuses on AWS. So we'll be looking at AWS CloudWatch to do that. Now, AWS CloudWatch can be ridiculously expensive, but there are ways that you can simply and cheaply use it to solve 80% of monitoring needs, which is plenty in a lot of scenarios. And if you learn how to set all this up in any tool, then you'll know what good looks like. And so you'll be able to understand whether you really need an expensive tool. And if you do need an expensive tool, having an understanding of what you're looking for will help you negotiate a good price with the vendors. All right, I hope that this presentation gave you a better understanding of what monitoring and observability are, and from a practical standpoint, how they're used in a workflow. And I hope you're excited for this unit because we're going to be setting this up to a very thorough degree and arm you with some principles to help you understand how to monitor and what you should monitor in any system that you make. Very cool. Thanks for watching this video. I will see you in the next one.